Then, today we're actually quite happy to have my colleague, Qimiao Si, to give a talk on the high temperature superconductivity in bilayer nickelates. And Qimiao is well known in the community for working a lot on ion-based superconductor and quantum critical point in the heavy fermions. So today he's going to try to educate us on what his opinion on high temperature superconductivity in bilayer nickelates. Yeah, thank you, Qimiao. Yeah.
Thank you, Pencheng. Yeah, so thanks for the invitation first. And I think this forum is supposed to be having the pedagogical aspect. And I thought about what to say, and that maybe it would be good to sort of introduce the problem, injecting a bit of my bias into the problem, and we'll go from there. So the topic is bilayer nickelates and high temperature superconductivity in these. And I will actually stay with pretty much within the bilayer nickelates, but certainly there are cousin materials that exist and are being extensively studied. Before I go further, let's see, my cursor was working. Let me try one more time. Okay, it's no longer working. So let me do this. Let me acknowledge my collaborators. So this in my group, Yiming Wang is a graduate student, Kwang San Ling is a postdoc, and Lei Cheng, before he left for Stony Brook, he's being actively involved in this work. And his work has been quite extensively in collaboration with the group of Rong Yu, my long-term collaborator who is now based in Renmin University, and his graduate student and postdoc is Jiang Liao and Gui Jin Duan. So let me just to see whether, oh, good, control is back. Nickel-based superconductivity was a course of long slog, and so the heroic effort of Harold Huang and others in the community who realized superconductivity in the films of infinite layer nickelates. And this is a typical phase diagram of this infinite layer nickelate. TC is somewhere about 15 to 20 Kelvin, and was discovered at a time where sort of the age has reached a bit of the school age. And as the color plot showcases the different regimes, including the characteristic dome of superconductivity. X here marks the usual doping through substitution. And it was not quite a coincidence to showcase a phase diagram like this, because part of the pursuit was to see whether the cuprates have counterparts in other families of materials. And in a bit of oversimplified picture, perhaps superconductivity in these nickelates are natural, in a sense that if you count the nominal valence, you end up with 3D 9 valence, the 9 electrons in the 3D orbitals, and that for the parent compound, and that has some degree of similarity with the cuprates. And substitution is not the only route to realize a phase diagram like this. This is the Harvard work in this particular what's called a square planar series, where again you can without any substitution, but you can change the n and count the nominal valence, and to see that going from infinite layer limit to n being finite, and you can change the electron count in the d electrons. So a feature like this for the superconductivity, Tc versus n, can be considered as analog of the well-known phase diagram of the cuprates as far as the doping count, the electron count is concerned for the whole doped side. So that's the infinite layer nickelates and related series. The more recent work discovery was on this bilayer nickelates 327. This is in this Ruddlesden-Popper series, and Tc under pressure reaches on the order of 80 Kelvin, and there's a number of other features in this phase diagram. There's some changes of different kinds. There's going from weakly insulating regime to the metallic regime in a normal state. And initially, there was a considerable challenge with the materials, and there was some discussion about whether even zero resistivity has been achieved, or what's the volume fraction and all that. And in the intervening time, mostly these issues have been sorted out, and I think this phase diagram more or less stood the test of this short period of time. And so superconductivity under high pressure, that has been extensively studied in a variety of materials in the recent past. Having such systems showing superconductivity at such high temperatures certainly generate a lot of excitement. And although the fact that this is happening, let me get to the pointer. It's happening at such high pressure certainly represents a challenge in probing a variety of properties that we would like to know in order to gain understanding of this system. So with that in mind, a fairly drastic breakthrough happened late last year, earlier this year, where instead of working at a 14 GPa or some such pressure range, one could work at the ambient pressure by putting these bilayer nickelates in contact with substrate in the films, and the compressive strain realizes superconductivity at ambient pressure, and one could this films also allow some tuning of structurally. The compressed film, the strain is such that unlike pressure, the C-axis is actually elongated while the AB plane is compressed, and I'll come back to the relevancy of that to the electronic physics. And there's also various things that one can do, annealing, etc., that allows for carrier doping. So the upshot is that superconductivity still is happening at very high temperatures at around 40 Kelvin also, and this is another showing of zero resistivity in these films, and there have been a number of groups who have realized this kind of films with superconductivity at ambient pressure. So that's very exciting, and I will come back to some of the properties that become, including the properties about the superconducting state that have become accessible due to the realization of these ambient pressure, ambient condition superconductivity. So coming back to this overall set of materials, the let me just put some perspective and bit of my bias into this. So when I first heard this the bilayer, the superconductivity, the report of superconductivity at such high pressure, I remember talking to a number of people, in particular with Chandra Varma, and we took the normal state of resistivity and extrapolate that to the zero temperature, and we found that that extrapolated value is only 4 times of what the measured low temperature resistivity. So there seems to be some one could have put in some skepticism of the initial result, but as I mentioned, that has been sorted out. Zero resistivity certainly has been achieved through the work of Zhejiang University and ILP. So if we take a phase diagram like this seriously and look at things like strange metal labeling and overall phase diagram, the pressure scale, the temperature scale, one could say, well, maybe it's quite sensible because this is a 20 GPa. If I put phase diagrams like this for heavy fermion superconductivity, this is the phase diagram from Los Alamos, cerium, rhodium, indium-5 under pressure. Instead of 2 GPa, you scale up by a factor of 10, and instead of several Kelvin of TC, you scale up by a factor of 10 or so. And so maybe it's natural without thinking too much about the microscopics. In a slightly more specific fashion, and I'll talk more about this. The ion-based superconductors certainly has been extensively studied over the past decade and a half, slightly more than that. And one of the features that happens that characterize ion-based superconductors is that if you look at the room temperature resistivity, it's reaching or surpassing the Marty-Ioffe-Rigo limit. And so it is a bad metal, and that certainly is a feature also shared by these new analogy goes somewhat further, and before I get to that, this was May 2023, just immediately before the announcement of the superconductivity in the nickelates, and Nigel Hussey and I had some summary and perspective and thoughts about ion-based superconductors, and one of our comments was that that one of the legacies of ion-based superconductors is opening up a new regime of the parameter space that allows one to draw some lessons from these ion-based superconductors, from a study of ion-based superconductors that might be of relevance that could shed light on a slew of emerging superconductors. So, in what sense this link could be made? The bilayer nickelates, if one counts the valence, one ends up with the conclusion that instead of having nominally 9 electrons or 3D orbitals, you have a 7.5 electrons in these 3D orbitals. And one can look at the electronic structure in some detail and reach the conclusion that the dominant electronic states near the Fermi energy are the nickel EG orbitals, the 3D EG orbitals, while the T2G orbitals, the 3 T2G orbitals are substantially away from the Fermi energy, and so are the oxygen p orbitals. And and the other orbitals are even further away. So if I say that the three T2G orbitals are fully occupied, and then we have 1.5 electrons occupying the two EG orbitals, and considering that this is a bilayer system, so there are two of these nickel ions in each unit cell, we count to three electrons per unit cell distributed in the four EG orbitals. And how do we, it's a partially filled system. How do we think about the problem? We can take the perspective that the interactions are very weak, in which case, well, we need to take into account the level of spacing, etc. But including such effects, one can think about three electrons to be spread out in all these four orbitals, or so from the lessons we've learned in the study of ion-based superconductors and other multi-orbital systems, that if the coupling is not weak, it could lead to the interactions could lead to the differentiation of the orbitals, and even though one is in the incommensurate filling situation, some of the orbitals could be closer to half filling than the others, and pick up a stronger interaction effects. So this is general consideration, and at the very beginning, there were very few characterizations of the system. What there was in at the ambient pressure, and I want to single out this measurement from Haihu 1 on the optical conductivity, because it played a very important role in our thinking about the problem. And so this is the optical conductivity, sigma 1 omega versus omega, and put in here, there's some band structure calculation results based on the DFT calculations, and then there's a measurement. Precisely which part should be counted as a Joule part, etc. That's a little bit a complicated issue in these multi-orbital, multi-band systems, but one can get the order of magnitude of the Joule weight. And the measured Joule weight is substantially smaller than the non-interacting Joule weight. And so one could put this ratio, the measured Joule weight, over to the non-interacting Joule weight in a chart like this. If you for the cuprates at half filling, it would be a multi-insulator, so it would be, this ratio is 0. The very weakly interacting systems like silver, copper, what you measure for the Joule weight is roughly what is expected from the non-interacting band structure. So this ratio is 1. So very good metal, multi-insulator, and clustering around here would be a calibration for the typical bad metal behavior. And these are kind of things that were also used as a meter for calibrating the strength, the effect of interactions for the ion-based superconductors, and the nickel-based superconductors seem to belong to this this bad metal regime, as at least based on this calibration. So this guided our thinking, and we decided to take seriously these multi-orbital models, putting in the Hubbard and Holmes interactions, and ask what type of correlation, what the kind of perspective we should take about the correlations in some detail. So one of the features that's important to this bilayer nickelate is that if we involve the two orbitals I mentioned, the 3D z square orbital and 3D x square minus y square orbitals, the z square orbitals has the geometry such that the interlayer coupling is expected to be stronger than the 3D x square minus y square orbitals. So in early going, we thought we don't want to deal with this full orbital model for 3 electrons. We thought we were not alone on doing that, but we did that as well, namely considering that this coupling, kinetic coupling between the dz square orbitals across the bilayers to be sufficiently strong that we only need to worry about the bonding combination and just throw away the anti-bonding combination. So it becomes a simpler problem of 3 electrons occupying 3 orbitals in the unit cell. And this is, so as I said, we're going to, in the initial calculation, we decide to throw away the anti-bonding orbital, but we keep the Hubbard interaction, the Hons interaction, and studied this multi-orbital Hubbard model using some auxiliary particle representations, specifically this U1 slave spin representation, and carry out the saddle point calculation. So this is the overall phase diagram that we determine. U is the Hubbard interaction, and the vertical axis is a ratio of the Hons coupling to the Hubbard interaction, and it is believed that the realistic interactions for the nickelates is somewhere in this blob, and you can see that in this blob corresponds to the regime where there's a strong orbital selectivity in the correlation effects, meaning that the quasi-particle renormalization factor between the different orbitals are substantially different. And so this gives the encouragement to proceed and do more systematic studies of the correlation effect, and in such a way that, again, it's early going, and so we want to orient ourselves, and the way we orient ourselves is to carry through these orbital selective correlation calculations and see how it compares with spectroscopy results. So this is now going back to the bilayer 2 orbital Hubbard model. So the dz square, dx square, 3dz square, 3dx square minus y square orbitals per nickel, and so there are 2 nickel and therefore 4 orbitals. And we allow all the 4 orbitals to be in the mix, and there's some, in addition to general characterization, there's some particular motivation of comparing with experiments, and I'll come to that shortly. But this is the result of calculation for n equals 3, 3 electrons occupying these 2 sets of d orbitals. And so this is a physical filling case for the bilayer nickelate. And the renormalization factor, Z is the quasi-particle weight, U equals 0, it is in the interacting limit, Z equals to 1. And in the relevant interaction range, we show the result of the renormalization factor for the 3D x square minus y square orbitals, 3D z square orbitals in the bonding combination, and 3D z square orbitals in the anti-bonding combination. To gain a wider perspective, and also to put other cousin systems into the mix, such as the trilayer nickelate, which has since also become available. we in the model calculation, we allow ourselves to go away from the physical n equals 3 electron filling case for and say this is the n equals to 3.5. Qualitatively, similar features persist. The differentiation between the renormalization factors, the correlation effect in the x squared minus 3d x squared minus y squared orbitals versus the 3d z squared orbitals. And we can match further to n equals 4 electrons in these four 3D orbitals. And so there's still the differentiation of the renormalization factors among different orbitals, but the system being at half filling can get into the mod insulating phase in a much more ready fashion compared to the other fillings. So if we put all these together qualitatively, n equals 4 is the half filled case where we have the metal and the mod insulator, and n equals 3.5 is here, n equals 3. The physical case is here, and ambient pressure, ambient condition to apply pressure case would represent a tuning like this. And so the upshot is that there's the orbital-selective mod phase sitting at sufficiently strong interactions, and for the relevant interaction range for the physical n equals 3 case, we're outside of it, but we're still experiencing the inference of the orbital-selective mod physics as manifested in the strong orbital dependence of the renormalization effects. And so that's the qualitative conclusion, which we want to use to guide our own perspective about the physics here and the physics of the cousin materials. So for example, if I want to think about the physics here, I could use this anchoring regime and perturb away from it, and provides a way of thinking about interaction effects. In further detail, I now stress the z square, 3D z square orbitals are more correlated, experience a strong renormalization effect, and that will become important when we and think about the spectros in connection with spectroscopy in a normal state, but also in connection with the kind of superconducting pairing state that can develop. And also, I already mentioned that by looking at the problem over this the wider perspective of the electron filling and interactions, we can find some anchoring regimes to think about the physics in the physically relevant regime. So this is the overall perspective, and I want to get a sense of whether we're on the right track by comparing with the spectroscopic measurement results. So first, in a single particle spectrum in our calculation, from comparing the electronic states, the energy dispersion in a non-interacting case in this relatively narrow energy window near the Fermi energy versus the result of the calculation in the presence of interactions. Two things are reasonably apparent. One is that you can see that overall reduction of the overall band width. And the second thing, which turns out to play a very important physics, is that in the non-interacting bands, the 3DZ square states are crossing the Fermi energy. And in this particular calculation with the particular level of separation, etc., that's put into the calculation, the 3DZ square band states have the bonding ones have mostly been sunk down below the Fermi energy, although not drastically. So whether the 3DZ square states actually are below the Fermi energy or crossing the Fermi energy seems to be very important, as we are also learning now we as a community are learning now from the measurements in the films at ambient conditions. So I'll come back to this point, but I want to stress this feature, which also very much is sensitive to the orbital-selective renormalization, in addition to the interactions that gives you the overall band width reduction. So let's dive a bit into more details. This is the APAS measurement of Xinjiang Zhou's group, and these are cuts that in the Briand zone that you don't have to pay too much attention, but the point is that one can probe the dispersion for this inner pocket, which is primarily 3D x square minus y square orbital contribution. And one could take the cuts that's probing primarily the red one here, which are primarily sorry, the color is a bit, these are the z square states. And so you can, the numbers here gives the or the inverse of that is the renormalization factor. Can just use these numbers. And so experimentally, it's clear that indeed z square orbitals have stronger renormalization. Experiment is also showing that in this material, at least, the z square band has sunk below the Fermi energy. So we did some more detailed analysis of our calculation, and the aim was not so much to achieve quantitative consistency with the experiment, but to sort of qualitative and semi-quantitative consistency. And so the conclusion that the z square states experience stronger interaction renormalization than the 3dx square minus y square orbital. These are the theoretical calculations at n equals 3, n equals 3, n equal to 3.5, different values of the interaction with the Holmes coupling fixed at about 20% of U. And so by and large, this is consistent with the trend of the measure of this particular measurement. And so that gives us some confidence in thinking about the problem from this perspective, and these conclusions about significant correlation effects and significant orbital selectivity in the correlation effects. So this is the single particle spectrum. We've come back also to look at a bit more details of the optical conductivity, the reduction of the spectral weight in our calculation. We also find in a reasonable the interaction range. We found that the calculated Jude weight for in the presence of interaction is about 30% of the non-interacting result. Experiment the precise value depends on what part of the measure spectrum is lumped into the Jude part, but by and large, it's even stronger. So maybe there's some details that's still missing in the model, but at least trend-wise, the system is not weakly correlated. I think our calculation compares with the experiment, certainly is consistent with the conclusion that there's substantial interaction effect by analyzing the Jude part of the optical spectrum. The finite energy part is also interesting. because it has been emphasized experimentally that this part seems to be hardly, at least not drastically renormalized in the measured spectrum compared to the non-interacting spectrum. And we found that if the bounding 3dz square states are pushed below the Fermi energy, this is the situation that's realized. If the bounding 3dz square states are above crossing the Fermi energy, this 1eV feature staying roughly or very weakly renormalized from a non-interacting result is not as robust. So in that sense, this finite frequency part of the optical spectrum is also very informative, reflecting what these dz square and these different 3D states are doing in real material and in the calculations in the presence of interactions. And we can propose one more test, which is that in addition to the conductivity that's measured with the polarization in the plane, it would be also instructive to do measurement for the polarization along the z-axis. And this is a calculated spectrum in the interacting case, and it will be instructive to see experimental measurement. To my knowledge, that has not been measured yet. So this is all that I want to say about the normal state. I want to now transition into the consequences of these considerations for the pairing state. And so what we've done is, again, using a perspective that's anchored by this overall phase diagram, even though the system is metallic. It's bad metallic, but it's in proximity to this orbital-selective Mott regime that one can use this hypothetical orbital-selective Mott phase as a starting point, do pressure tuning, do doping variation, and presumably realize this superconducting part of the phase diagram. So with that in mind, using these as the anchoring point, we can construct the multi-orbital TJ like models and analyze the superconductivity. So this is the exchange interaction. And as I said, the Z square orbital is expected to have very large kinetic coupling out of the plane. And so that should lead to substantially J interaction. The X square minus Y square orbitals would also have this interlayer exchange interaction, but presumably weaker. And there are other channels of interactions in the plane. And we put a model, the multi-orbital Hubbard model in this effective TJ description, where the T part experiences the renormizations in an orbital selective way, as I already described for the normal state, and we state keep these renormalization factors as calculated in the normal state. There's also an important detail, which is how the 3dz square orbital and 3d x square minus y square orbitals, how the levels, the crystal levels, determine their relative separation. We believe that these details are actually manifested in a variable way in bulk materials, as well as in thin films, when for example, the c-axis lattice constants are tuned in a different amount, and I'll come back to that. And then the exchange interaction promotes the pairing, superconducting pairing. So this is the basis of all that I'm going to say for the remainder of the talk on the concerns of superconductivity. So if the exchange interaction, I'm going to construct a phase diagram in which the normalization is provided by the exchange interactions between the 3D x square minus y square orbitals in the plane. And I'm going to mostly look at the effect of interplane J for the 3D z square orbitals, and the interplane J for the 3D x square minus y square orbitals. And if this in-plane coupling antiferromagnetic nearest neighbor interaction dominates, it would expect to naturally to the D-wave pairing. If these interlayer coupling within the same site dominates, it would promote extended S-wave pairing, which will, of course, mix with the other extended S-wave components from the in-plane pairing amplitude, so long as they are in the same symmetry, irreducible representation. So one can group all these together using the irreducible representations. So the overall phase diagram says that there's a competition between the D-wave pairing and S-wave pairing. And so D-wave is illustrated in the standard D-wave pairing. And the S-wave pairing, extended S-wave pairing allows the pairing amplitude coming from these bonds across the layers. And the extended S-wave pairing is divided into two regimes. The regime where the pairing amplitude of the 3DZ square orbitals dominate for again this bond living across the planes, and separated regime where the 3D x square minus y square orbitals dominate the contribution to the pairing amplitude. Symmetry-wise, these two are the same, but they represent different regimes, and once one keeping track of the pairing amplitude of these different orbitals. It's again a lesson that was addressed quite extensively in the ion-based superconductors context. It was actually motivated by Pengcheng's neutron experiment in the ion-based ionic tides that we advanced this kind of different pairing amplitudes for different orbitals and how they would show up in the gap variation on the Fermi surface. And it was later on demonstrated in a fairly spectacular fashion in the STM measurement of the ion selenide 1-1 system by Seamus Davis and others. So conceptually, we want to analyze the pairing amplitudes of different orbitals, because that can have not only it would influence the condensation energy, but also it would be important in confronting with experiment. One bit of detail, but that's actually turns out important in understanding the gap variations on the Fermi surface, is that in either of these two regimes of extended S-wave, the interlayer gap function and intralayer gap functions turns out it pays for them to have opposite signs. And the reason it pays to do so is that it would avoid nodes on the Fermi surface. And that makes this opposite sign combination to have symmetry. Doesn't require that, but energetically it pays. So we in light of these film measurements on the superconducting state, it becomes meaningful to really think through about these gap variations on the Fermi surface. So D wave does what D wave does. It would have nodes. And for extended S wave, with the pairing amplitude predominantly carried by 3D x square minus y square orbitals, we found that the gap would be fairly isotropic on the Fermi surface. However, for the extended S wave, where the dominant pairing amplitude is associated with 3DZ square orbitals, we found that across the Fermi surface, there's a quite significant variation of the contributions from the different orbitals. And that leads to, at least compared to the other two, the D wave and the other regime of the S wave, extended S wave pairing, that has a significant variation of the gap. And so that's important in comparing. And one more feature, because we want to think about the films. And I already mentioned that the films are, of the bilayer nickelate are built in a substrate that compresses the nickelate within the XY plane. But unlike in the bulk systems when you apply pressure, where all the lattice constants are reduced, here because it's a strain, the C-axis lattice constant is increased. And so that makes this small details like crystal level, but this level separation between the 3D x square minus y square and 3D z square orbitals to be more variable. And in fact, there are seemingly conflicting conclusions even in the RPS spectrum for these films. And we claim that it's in fact natural because of this variation of the level spacing in the different films, and also the possibility of a different amount of carriers when you anneal or otherwise do something structurally or procedurally to these films. So here I'm illustrating one point that E is the level spacing. Delta epsilon is the atomic crystal level spacing between the 3dx square minus y square orbital and 3d z square orbitals. Delta E being positive or negative reflects whether the z square, the bonding 3dz square states are crossing the Fermi energy or has sunk below the Fermi energy. And these two things, just to highlight this particular variation, what consequence it could be when the dz square orbitals states are crossing the Fermi energy because of the larger the z square interlayer coupling, it's active. So that makes the extended S wave component, the pairing amplitude, to be stronger than the pairing amplitude of the same. Here we're analyzing the extended S wave case somewhere here compared to the pairing amplitude of the x square minus y square states, which are always crossing the Fermi energy. On the other hand, if the bonding 3dz square orbitals sunk sufficiently below the Fermi energy, the system, as far as pairing is concerned, cannot take advantage of the larger interplane J coupling between the z square orbitals. So that gives a chance for the x square minus y square orbital contribution to the S wave, extended S wave pairing to overtake the z square contribution. We've chosen parameters that is sitting here. One could also study regimes where the D-wave pairing is dominate is what's happening, and there's a somewhat related trend one could construct in variation in response to the tuning of the level spacings between the z-square orbital and the x square minus y square orbital. So here we're focusing on this, and the important point is that these different orbital pairing amplitudes will be manifested in the different variations of the gap on the Fermi surface. So for example, here are the two cases. In one case, we have the pairing amplitude of the z-square orbitals dominate. So theta 45 degrees is a diagonal in the square lattice notation. And so the gap, the orbital, different orbitals contributing to the pairing leads to a gap variation on the Fermi surface that has a reasonably substantial amount, but it goes this way. But in the other regime, which corresponds to here, the variation goes the opposite way. So that's a testable statement. And there are some recent experiments, not too recent, that at least in that particular film, the gap varies in a way that's compatible with extended S wave and with the dominant pairing associated with the dz square orbitals. Whether that and this is the Fermi surface characterization. So it's 45 degrees is the diagonal, and the variation is being shown in this span. Whether this, how much this says about in that particular film, whether the 3DZ bonding 3DZ square states are crossing the Fermi energy or not, that's a bit indirect, but it does give some hint for that part of the physics. And I want also emphasize that the significant variation of this pairing of the gap is associated with the fact that there are two orbitals showing two different and enough the distinct gap amplitude, and it should show up in some other spectroscopy measurements. And so this is there's some indication from, I think this is again Haihu-1's measurement showing that STM picks up signatures of two gaps. So I think the overall this is still early going, but I think the point I really want to make going through this in some detail is that the existence of these films and the superconductivity at ambient conditions, and therefore the access to the properties of the superconducting state is a major advance of this still very young topic. So let me just summarize. We took clues from spectroscopy experiments, some that exist at very early stage, some has come up in the since that time, and I emphasize for the normal state on the implications of optical conductivity and angle resolved photoemission spectroscopy, and how that has, at least for us, anchored our theoretical considerations, especially concerning the correlation effect and orbital selectivity of a correlation effect. I stressed that we can look at the problem in a more overall way in terms of interaction strengths and electron filling that gives a perspective on the orbital selective correlations. We've done some work on the trilayer case. I've opted in just giving just a bit slower progression on the bilayer in the description of bilayer nickelates, but this overall phase diagram is instructive to think about the cousins of these bilayer nickelates. And this overall phase diagram also provides the guidance to think in terms of the multi-orbital TJ model, and that has served as a basis for us to think about the interplay of the inter and intralayer effective interactions. That's new for these nickelates compared to the ion-based superconductors, and that's manifested in the interplay between extended S wave and D wave pairing states. And I think I said enough times that the emergence of these thin films and therefore the realization of adequately TC superconductivity at ambient conditions is really a major advance experimentally, but also in allowing the theory to have sort of more direct confrontation with the experiments. So with that, thank you very much for your attention.
Thank you, Qimiao. Yeah, very nice. Yeah, any questions for him? Let me sort of ask the first question. So based on the structural analysis of this, compared with the cuprates and iron-based superconductor, can you actually speculate what sort of magnetism that can sort of precede as a parent compound? I mean, based on the theoretical.
So
because in iron-based superconductor it was speculated, right?
Yeah, so it's a very important question. So if you look at the phase diagram, like actually, let me put this chart here. So I think it's been historically known at the ambient condition, there's a phase transition around I forgot, I think that's around 130 Kelvin or so. And there's been a lot of progress. There's X-ray measurement has giving the report of the detection of the dispersive spin excitation. So presumably spin is involved in the ordering, and whether orbitals are also involved in some way, I think that's less clear yet. And certainly the historical static susceptibility measurement also indicates that there's a strong spin interactions. So I think the short answer is, at least to my knowledge, it's not being fully clarified yet. But
no, I understand that's not known.
Yeah.
Fundamentally, I'm just asking a theoretical question, right?
Yes.
Do you have any speculation from theory perspective?
Yeah. So no, we should. I mean, we've been sort of focusing on slightly different aspects, but the model also contains the information about spin ordering, orbital ordering, and all that. So
so you don't know yet.
We're in a position to study it. We haven't gotten it.
Okay. Thank you. Yeah.
It's a very important question.
Yeah. Okay. Yeah. Any other question? Jeff, you have a question? Oh, you're muted, Jeff.
Yeah, I've been working recently on another copper type system, which is silver, and silver in the D9 configuration, which is kind of an interesting thing. I didn't know until recently that any silver compounds ordered magnetically, but this one, and it's also an alter magnet. So then the question is, maybe there's a different avenue to study these materials. So we don't know if you can dope it and make it superconducting, but that's kind of interesting. It's kind of interesting because copper was a totally boring element. Everybody knew that nobody cared about copper magnetism until the mid 1986, 1987, and all of a sudden copper is the most interesting magnet on the planet, and then
30 years, for 30 years,
and then so and then until iron, of course, so iron's always been interesting, but the interesting thing is, of course, silver is right below that, And
I see.
Yeah, that's very interesting.
So yeah, so that's
Well, Jeff,
anyway,
this is very interesting. Actually, it reminds me that what I should have done is actually to give some of the theorists some credit in motivating the nickel study, right? So people like Warren Pickett and T.M. Rice and
this even preceded
and others certainly has so give the theoretical community some credit. Silver, I don't know how to think about it. Yeah.
Other theorists.
Other theorists.
Other theorists, yeah.
Well, yeah, the community needs some credit, whichever way.
Yes,
I agree.
Yeah. So anyway.
Okay. Any other question for Qimiao? Okay. Well, it's a very clear talk. Yeah. Thank you, Qimiao.
No, that was great. Yeah. Thanks very much.